Okay, and then the next commands are really simple commands, just for adding, removing, or updating data. And so this is the first command to insert a row into a table. And so that means values. So you once define the table with create table, and then the schema is fixed, and then you can add, remove, or update rows. So with insert, you define the table name, then the columns you want to specify values for. It can be a subset of the columns, and then other columns get default value or null, and special value meaning that the value is unknown, and then you specify the values. So for instance, to insert a row in the supplier table, you specify the columns of supplier and then all the values. So snum gets the value S99, Watson is the supplier's name, 25 is the status, and Oslo is the city, and then it gets added to the table. And so not really complex. The second command is update. So there you update the table and you change the value of some column or multiple columns, and then you use a where, and where always specifies a condition. So which rows you want to update. So here's a simple example. We update the suppliers table. We set the status to 100, where cities and Athens. So actually, where is executed first? So first we identify the row matching the function, and it can be any predicate. So here it's on a single column. It can also be where snum is S5, or where snum is S5 and name is Adams, sname is Adams. So it can be anything, so as long as it identifies one or more rows, and then you update status. You set status 100, and then this column changes its value. So any questions about this? Pretty easy, Okay. And then with delete, well, it's the same, but then you delete rows. So for instance, you can delete the suppliers where the city is Paris. In this case, it actually matches with 2 rows, so that's also possible. And then you delete these 2 suppliers from Paris. So if I want, for instance, to remove only 1 supplier, I can define a condition using the primary key. I can say where snum equals S1, and then it will only match a single row. Yeah.
The label in the data states quantity.
Yeah, I know. It's a mistake here. Yeah. So sorry. Okay, indeed. So this should be city, and here also in the previous slide also. Yeah. Okay. So you have referential integrity. So referential integrity is a fancy term for just saying that you have to be careful with foreign keys, because you have a foreign key. That means you have a link to another row, and that link cannot be broken. So for instance, if I delete supplier where snum is S1, there can be a conflict, because it could be that there's a shipment records from S1. So I cannot remove it because the foreign key, or referential integrity, defines that every time you have a foreign key, that value must exist. You can only reference other column values if they exist in the original table. So if you try to delete it, then it will say something like delete statement is in conflict with the reference constraints or the foreign key constraints. And so one option would be to first remove from shipments all the shipments where snum S1 is a supplier, and then if there are no more references to that supplier, you can safely delete it. So that's a two-stage process to delete it that you might want to do. And so in general also, if you're doing insert update or delete, it will always check everything. Like if you insert here snum, for instance, if the primary key is not unique, you will get a warning. If Watson is not a string but an integer, you will get a warning. Yeah. Also for shipment, if you want to insert something in shipment, it should be a valid supplier in the supplier table, a valid part in the parts table, and a valid project number in the project table. And so that's all checked. Okay. Okay. Those are the update instructions. And then we can query data. That's done using select. And so it's always select from where. In the from statement, you write the table name. In the select, you write which columns you want to return. And in the where, you write your condition. So some examples of that. So very easy. Select sname, sname, and status. So these are the three columns that you want. The other columns are ignored, they are not returned. From the suppliers tables, where the city is London. So first it matches the where condition. And so in this case, it's S1 and S4 that are suppliers from London. Then you return only these three attributes. So that means in this case, status is status returned, but city is not returned. And so that's why you get this as a result. And so it's always the same format. Select which attributes you want, from which tables you want, and then the conditions. But that can get quite complex. So some more examples. So one type of complexity that we introduce is the join. We already saw some examples where you need data from different tables. If you need data from different tables, you're going to join them. And joining is the same like an intersection. If you have in mathematics, you do the intersection of two sets. But here the intersection is based on the primary foreign key relations. And so here's an example. And so, for instance, I want to supply a name and supplier city, but also the shipment quantity and the shipment timestamp. So here, supplier name and city are from the suppliers table. So that must be in the from. And the second table we need is the shipment table, because we want the quantity and the shipment timestamp. But then we do an inner join because we only want rows, or combinations of rows of both tables when the join condition holds. So this is the join condition. And so that means the supplier sname must be equal to the shipment sname. And so it's very, very simple to express. And this way, and then you can have additional conditions. So here you're only interested in the first supplier and you get this result. So if I go to the next slide, you see an example. And so I have my two tables. And so from suppliers, I want, what was it, sname and city. From shipments, I want the quantity and the shipment timestamp. But I want to join those two tables, so that means the snum in shipment must be equal to snum in supplier. And if you write that down, it's inner join, where supplier snum is snum, you get that condition. And then there's an additional constraint in the where, namely that the snum must be equal to S1. So in this case, we just get all the shipments from Smiths. You can do the same with and then join, for instance, some parts, and then you get all shipments from a certain part. Then you get the additional attributes of parts, or you can join with projects, and then you can get all shipments of a certain project, and so on. Okay, so this is extremely important because if we denormalize the data, we need to often express joins. This is on two tables. I think a more elaborate example I shown before, that was this query. So here, actually, if we want a big table, we can just join everything. We can join shipments with suppliers, where shipment estimate is equal to supplier estimate, and then join that result again on part, where shipment P is part number, and then again on project, where J equals project J number. And then we get our big table from the beginning, from the denormalized perspective. This one. So these are joins, and yeah, they're a necessary evil if you store the data in this normalized formats. Okay, so some types of joins. You can do the inner join, which is the one I showed before. Sometimes you also want to do a left join. For instance, you want to left join a supplier with shipments. Then even if a supplier doesn't have a single shipment, it could be the case, you still want to include the supplier, but have null for the other attributes. That's called a left join. So that's one example. So imagine you have five suppliers, but one supplier doesn't have a single shipment. If you just do a join, yeah, it's not in the result set because it's not matched with the single shipment. There's not a single shipment where the supplier ID equals the one from the supplier table. So you kind of leave that out. But if you want all suppliers on the left side, you should do a left join. Yeah. Yeah. So the join condition, it's always on the intersection. And the only difference is now that if there's a row, a primary key which is not being referenced in the second table, then we still include it. So that's why the Venn diagram. The Venn diagram is used as an illustration of that. And symmetrically, we can do the right joint, and so that has the same semantics, but on the right-hand side, or the full outer join. And then we don't lose any data in case there's no intersection, so in case some attributes are not missed. That's a special type. So inner join is used the most, sometimes also left join. Yeah. Okay, and then our last query, and there are more types of queries, but this is the last important variation, is to get some summarized data. And so with summarized, I mean counting how much a certain value occurs, but you can also have the sum or the maximum or the average or the minimum, and these are the other aggregate functions in a certain table. So if you just forget the group by statements, you can compute a minimum, maximum, or average over an entire table, over one column. But often you want to group it. And with grouping, I have an illustration. And like here I select city count star from supplier. I group by city, and I having count bigger than 1. And so this is the result. And so what does this mean? Why does it says London 2 and Paris 2? I'll let you think about it. Yeah.
Two rows with that contain London, and there's two rows that contain Paris. The last one is one, so it doesn't fit count.
No, indeed. So indeed, so you can the group by actually, if you look at it like this, first you create groups, groups that share the value of a certain attribute. So in this case, the city. So you boost these two rows, the single row, and then you compute statistic, but over each group. So that's the meaning, and that's a very useful operation because often you want that the number of students in each master, the number of the total amount shipped from one product, or the average price of products being shipped, and so on. And so that's one way to compute statistics, but conditional on a certain column value. Okay. So yeah, as I mentioned before, queries can get very complex. So a query with hundreds of lines is possible in the real world. And so this is an example when I was working at Frumal 3 years ago. So here you do in the front, you have two bigger tables, but then here you see some time manipulation, and that's often something that introduces quite some complexity. Here also, I'm only interested in 1 week of data. So here's a filter on dates, and then there's a filter on other things, and so on. And I want to order my data. And so these in the real world queries can get quite complex. Okay. Yeah. Okay. I still no. I have still half an hour left. Oh, we're on time. Okay. So actually, that's all I wanted to talk about SQL. So that's the main thing. So also for the exam, expect some open queries. Not too difficult, but still. And also in the lab session, you will practice some more queries. And now the last part is a little bit on the inside of the database management. So as an end user, if you use a database, you can just use SQL. But let's also peek inside the database and see what's behind the curtains. So a little bit technical. And actually, there are two parts. Database management is a complex software system, but there are two parts that I want to show. These are the transaction manager and the query optimizer. So let's start with the transaction. And so here's an example of a transaction. And so it's very simple. I have an accounts table where I have different accounts, and I have the balance. Actually, the columns should be switched. So I have a bank account 1, 2, 3, 4, 5, 5, 5, 5. And I have a certain balance on the first account and a certain balance on the second account. And one transaction would be to transfer, in this case, 200 euros from 1, 2, 3, 4 to 500. And obviously, that's only possible if the current balance is higher than 200. Actually, it can be higher or equal. Small mistake. So in this case, the current balance is 259. So that's higher than 200. So I can withdraw 200 euros and deposit it in the other accounts. So this is a transaction. Usually, if you program this, and you have here the update statements 2 times with different where condition. And so this subtracts 200 euros, this adds 200 euros, this selects the current saldo, and I have this condition to see if I have enough on the from accounts on 1, 2, 3, 4 to actually allow this transfer. And you have start and end transaction, or begin and end, which is also something you have to declare. So what can go wrong? Yeah, the first thing that can go wrong is I execute my little transaction. It checks my balance. It's okay, I have more than 200 euros. Then I update the account and I subtract 200 euros. And then somebody at the bank pulls the power out of the server. And then, yeah, you lost 200 euros. So that's something you don't want. So that's something you want to prevent. So what else can go wrong? Suppose at the exact milliseconds, so computers are very fast at communicating, but within 1 millisecond, let's say I have two bank cards, I give one to you, and we talk over the phone. You withdraw money in Ghent, I withdraw money in Antwerp. It could work, right? If we're really fast, you could withdraw 200 euros in Antwerp, I could withdraw 200 euros in Ghent, but the end will be negative. We will have minus 141 euros. So that's something we should also avoid. So we call these two concurrent transactions. And yeah, if they occur at the same time, both are a success because you first do the check and then you do the update. So the check passes, both of them, then you do the updates, then it could, allez, it could work, but we want to avoid it. So these are two issues. So and we call what we have is a transaction manager. So the first rule is you have a transaction and either it commits or it's aborted. So commits means all the results are saved on disk in a consistent way, or that's the second case, it's aborted, meaning it's rolled back, meaning all partial changes are undone. So that's what you want. You want all or nothing. Either the update, the withdrawal and the deposit both occur together, or none of both operations occurs. And so we call that acids. Acid summarizes the properties of the transactions. And so the first one is atomic. And so either transaction performs as a whole or it's completely undone. And so that's the atomic property. Consistent means that after the transaction is executed, the database is left in a consistent state. Meaning consistent means, for instance, all foreign keys are still valid and so on. And then durable. Durable means if a transaction is completed, so committed, it cannot be undone. So it means it's safe to disk. Even if you shut the server off, it's still durable, it's still persistently saved. And then the third one is isolated. That means that transaction seem to be executed in isolation. So that means if they are running in parallel, they do not interfere with each other. So that's a rule. So you can not only access the changes if they have been committed by another transaction. And we'll see an example of that in the next slides. And so the transaction manager also uses an algorithm. It's two-phase locking. So it's very, in essence, a very simple algorithm, and it ensures isolation. So that means that if you have concurrent transactions, it seems like they're that they're run sequentially. The algorithm for doing that is called two-phase locking. So if you want to read data, you take a read lock, and if you have to write data, you have a write lock. And if you have a read lock, that means other people can also read the same values, but they cannot change those values. And the reason why you allow that is you want to maximize concurrent working. If two people both want to check the balance of a certain account, they should be allowed to, because they don't interfere with each other. But the second condition, the second type of lock is a write lock, and there it's important. So when you start writing to a certain row, then other transactions have to wait until the lock is released. So it's like a physical lock, in this case, if you have two transactions that update the balance, the first check that passes in both, because they both read the current balance, so that's allowed. But then if the first transaction tries to write to the balance, that means other transactions at the same time, that are running at the same time, cannot access that data anymore. Because you have a write lock, that means no other transaction can read the same data or write also to that row. And so the row is in some sense private. Only one user can access that row at one time. Obviously, in computer terms, this means you have to wait a number of milliseconds, and then the other transaction can continue. So that's the idea. And then you don't have that problem with the concurrent transactions. And so here's another illustration of that process. So we have our two transactions running in parallel, and here we have the table. and it summarizes what is allowed and not allowed. So if both transactions read the same value, that's allowed. If one transaction writes the same value, and the other one cannot even read that value. And why? Because if it reads the value, it might be it's an uncommitted value. And the first transaction is changing the data, but it's only after the transaction has completed and has committed the results that the second transaction is allowed to read that data. And then the other way around, you can also read and write. The other way around, it's also not allowed, or write and write. And so you have some operations that are allowed, but once you start writing, basically you're going to lock those data elements. You see an example here. So here, the first transaction starts. You acquire a lock. That's why it's called two-phase locking. First, you acquire a lock balance for reading balance. Then you're going to ask a lock for writing to balance because you're going to update the value. Then you're going to ask for a lock for the second balance that you want to change. So you also have a lock. Then you release all locks, and then you commit the transaction. And so what happens if the second transaction is started in parallel? The transaction starts, it reads the balance. At that point, that's okay, because there's no write lock, there's only a read lock on the same balance. And then it wants to change the balance, so it asks for a write lock, and that's not allowed anymore. And also the other way around, once this transaction asks for a write lock, it's not allowed, that read lock does not allow that anymore. So what happens? Yeah, there are two options. Both are cancelled, meaning all partial results are also lost, or one transaction is cancelled and the other one can continue. And so that's what you want. And so our idea of going to Ghent and Antwerp probably doesn't work. Hey, we can try it if you want. Yeah.
So in the first transaction,
yeah.
The value is 2, like let's assume it was 0, for example.
Yeah.
And he was expecting the 200 euros, and then when I did the transaction for 200 euros before the first balance of 200 comes into his account, or maybe more, it goes into negative. So wouldn't you lock both of them at the same time? So also balance should be locked with any withdrawal transactions?
Wouldn't you lock both in the same time? The idea of having these partial locks grow is that you maximize concurrency. You want to maximize the number of users that at the same time can access or change data. So that's why it grows. The two-phase locking algorithm grows. You start with a read lock, then you promote to a write block, then another write block. So it grows. But it doesn't matter that much. You could all do it in the beginning, but it wouldn't be more safer than doing it incrementally, because at the end, you're always going to stop other transactions once you have acquired a lock. So you don't need to lock everything at the start. That would be an easier algorithm, but that would not be safer. It would be exactly the same result, and it would have a performance hit because less people would be able to do things in parallel. It's an excellent question. Yeah. Okay. So that's actually what I wanted to say here. So the two-phase locking algorithm guarantees that transactions are executed serializable. So that means in a serial way. So if you have two concurrent transactions that are planned using two-phase locking, this guarantees the isolated nature of firstly executing T1 and then T2. So there's one risk, and that's a deadlock. So a deadlock happens when you have a transaction which has some lock, and then it has to wait on the second transaction, and then the second transaction also has some lock, and it waits on the third transaction, and then the third transaction has a cycle back to the first transaction. And so that's a possibility. And so a trivial solution is to have some kind of a timeout. It's like you wait a couple of seconds, And then if no lock is released, you abort the transaction, and then you have to redo the transaction. So that's one trivial solution to deadlock. Also in NoSQL, so that's for next week. So other types of databases, not based on the relational model. You have some alternative concurrency control algorithms that make a different trade-off. So not with a focus on isolation and more focus on performance. So more throughputs, lower latency. And that's also a design choice you have to make as a data engineer. Do I need transactions? If you need them, okay, use a relational model. If you don't need them, use a NoSQL database maybe, because it's more efficient. And because the locking and transaction manager and so on, and also foreign keys checking, these are all operations that have a performance cost. So you have to make a trade-off there. Okay. Okay, so that was the transaction manager. The second insight into the relational database is the query optimizer and also indexes. So that's related to what we saw last week. So, like I told you before, SQL is a declarative program language. So that means you specify what you want, but not how it's implemented. And then internally, a database manager tries to find the most efficient way to execute a query. And that's the role of the query optimizer. Has the role to define like a plan, what's the most efficient way to execute a certain query. And it makes use of indexes. So we'll see what those are. So indexes support fast searching of a column value, and internally it either uses a binary tree or a hash table. So what we saw last week. So we use a binary tree, it's called the B+ tree, or a hash table for fast searching a certain value in a column. And it's especially important because we do a lot of joins. With the joins, you're comparing every row in one table against a value in the other table on the join condition. So that's something you want to do to be quite efficiently. That means with a fast data structure. So by default, primary key and foreign key columns are indexed. These are implemented as a special type of table, but you cannot access directly. It's only accessible internally in the database management software. And using those index, you can speed up selects, but each additional index also slows down the inserts, updates, and deletes. So it's kind of a trade-off there. And so creating the optimal set of indexes is an art, because you can set indexes on every column, but then your inserts will be really slow and your updates. And so that's also not what you want. So it's a little bit of an art. So here's an example. So I have my table here, and then I select the name and the city from users, where ID is 11. And so a trivial algorithm would read the entire table in memory, go row by row, and just select the users with ID 11. But that would be not efficient. So what we actually use is something like this. And so we have a B+ tree. It's like a binary tree, but in this case, it's not a binary tree, it's a tree-array tree. And so that means that this has the semantics. If a value, if the ID is bigger than 13, go to the right. If the ID is smaller than 23, go to the left. If it's between 23 and 31, take that row. If it's between 31 and 43, take that row, and if it's higher than 43, go that way. And so it's more than one split. You can, in this case, you have 3 splits. And at the lowest level, you have the individual users with their ID. So in this case, with binary tree search, it's smaller than 13, so I take the left branch. It's bigger than 7, 11, so I take the right branch, and then I have my data elements. And even if you have millions of users, if it's a balanced tree, the depth of the tree will be logarithmic in n. So that means only a small number of steps are needed to identify each individual record. And this is something you could keep in memory or keep in memory and not stored. And then the data, if your database is really large, maybe that's loaded from the disk. And so that's a B plus index. You can also have a hash table. It's the same idea. And so the query optimizer determines the most efficient way to execute a query, and it considers multiple query plans. So there are often different ways to get an answer to your query, and the query optimizer tries to select the most efficient way to get your data. And it takes the available indexes into account. Obviously, if you can use an index, that's far more efficient, and also the sizes of each table. So these are taken into account. And so that's an example, it's here. And so I have my user table, I have the address table, and then I here have a query. It's a join with a join condition. And so what does this query asks? What do you express with this SQL query? Yeah. Yeah. Yeah, indeed. Yeah. So it's a join between user and address, and restricted to users with a first name Niels. So how would you execute this query? What would you do as a human? What would you do first? Would you first select the columns? Would you first do this condition or this condition? What would you do? This one first, and then this one. Okay. It's not the correct answer, but that doesn't matter. But the interesting is there are two options, right? There are, you can first get all users that are called Niels, and then you could do the join, or you could first do the join, and then in the join table, you could filter on joined rows with username Niels. So these are two query plans, and the query optimizer tries to decide which plan is more efficient. Actually, you could be right, by the way. Allez, could also be correct answer. So here, it's just the opposite one I have in my slides. So it depends on the context. And so plan A would be to join all the users and the addresses, and that's efficient because the primary and the foreign key have an index. So you can do that efficiently. And then you can filter rows in the merge results where first name is Niels. If you don't have an index on Niels, that means we have to do a full row scan on the join table. So that's plan A. Plan B is the other way around. First, we filter in the user table those rows where the first name is Niels, and then we merge all rows where first name is Niels. And so both plan A and B compute the same answer, and then it could be that plan B is more efficient or plan A. It depends on the size of the table and so on. But the query optimizer estimates that. And based on this estimate, it takes the most efficient way. So that's not perfect. The query optimizer can be wrong, but often for most queries, it does a decent job and you don't have to worry about performance. So if your query is still too slow, one option is to add an index. So you have the command create index on table name. And for instance, here I select Niels from the table user. That means I check first name, so I can add an index on first name in the table user to make that type of query more efficient. That would be one way. And if you're using a database, you often have a special command. It's called explain. And explain gives you your query plan. So then you can look what is your database actually doing, and then you get something like this. And often there's one bottleneck, and then you can maybe investigate it and then add some more indexes to make it more efficient. Okay, so that's the query optimizer. And so some limitations of relational database management systems. And so often the data does not map neatly into rows and columns and tables. And also advantages can become drawbacks. So for instance, ACID transactions, so atomic, consistent, isolated, durable transactions, that has a cost. And if you have a large volume of data, that cost might be too high. Also, you have a static data structure. So if you have a domain where you want to add columns every day or every hour, then a relational database is also not that interesting. And finally, you have fast, efficient access to individual records, but maybe for OLAP, for online analytical processing, you want one big table. So every advantage can also be a disadvantage, depending on the application. And so that's why next week we're going to study not only SQL and also data warehousing. And so with data warehousing, I mean queries for business analytics. And with not only SQL, I mean databases with weaker consistency requirements. So as I mentioned before, checking transactions, foreign keys, joins, and so on. It has a computational effort. But for instance, in social media, and let's say Facebook, what if I post a message and then suddenly the message is lost because some server has rebooted or something? Okay, and that's still acceptable. And for Facebook, they don't care if somebody once every 1,000 of posts, one message is lost. That's not a huge problem. So actually, for social media, you can have a far more efficient system if you have weaker consistency requirements. The next typical property of not only SQL databases is web scale. And so you have queries in a relational database. We're often talking about gigabytes. With web scale, we mean really terabytes, petabytes, where you have a cluster of servers and the data is replicated on that cluster of servers. So that's for next week. Okay, I'm finished. Any more questions on relational databases? No questions? Okay, so lab session this week. Try to come. You can practice in SQL. This is also a nice website. If you're, we're also going to practice SQL Zoo. So there's some basic queries, like here, select a population from the world where name is France, and then okay, you have to write down something and then provide the correct answer. So where it's Germany, so I say where Germany. So that's a nice online system for SQL exercises, or you can just go to the lab session. That's also good. Okay.